CHEM 2100. This is our polymerization lab. We're going to be doing two polymer formations today. The first is going to be the synthesis of a polystyrene divinylbenzene polymer. This is thermal setting. We're going to deviate slightly from the procedure. In the procedure on ELC, it mentions using a hot water bath. We're actually going to use a hot plate set to 100 degrees. And we're going to place our 50 ml beaker directly on top. First thing that we have to do is set up our tinfoil cup. This is the form that we're going to be creating or setting our resin in, our polymer in. So we're going to take 2 sheets of tinfoil. We're going to press them gently down into the cup. We have to be careful not to rip the tinfoil as we do this. And I'm just pushing gently out on the sides, forming it to the bottom of our beaker. It doesn't have to be perfect. We just want to make sure we've got decent surface area. And this will allow us to take the resin out or the polymer out after it forms without having it stick to the beaker itself. Press it out to the sides a little bit more. Okay, I'm going to take it out just so you can see the form a little bit better. Okay, and I'll set that back inside. So this is what we're going to be pouring our starting materials into and then placing on our hot plate. Let's go over and measure out our reagents. So we have our starting materials. We're going to be using a mixture of styrene. We use 10 milliliters of styrene. We're going to mix that with 1 milliliter of divinylbenzene. And last but not least, we'll add 100 milligrams of benzoyl peroxide. We've already weighed that out. It's very difficult to see, but it's there on our weigh paper here, right along the edge. We'll add that in. That's our radical initiator. That's our catalyst for the reaction. I'm going to combine it into our 50 ml Erlenmeyer flask so that we can mix it up and make sure that our benzoyl peroxide dissolves before we start heating it. I'm going to be doing all of this underneath a snorkel. The smell from our styrene or divinylbenzene is very strong, so we want to make sure we have proper ventilation at all times. So we're getting 10 milliliters of our styrene. There we go. Again, making sure that we keep all of this underneath the snorkel. So that's our 10 mils of styrene. Set that off to the side. Now we're going to get 1 milliliter of our divinylbenzene. Okay, we'll add that into our reaction mixture. And now last but not least, we'll add in our benzoyl peroxide. Let me see it a little bit better against the glove. Okay, so we'll add that in just like so. And we're going to stir this for a couple of minutes to make sure that our benzoyl peroxide dissolves into solution before we pour it into our cup and begin the heating process. We'll check back in just a minute. So we've swirled our reaction mixture for several minutes. All of our benzoyl peroxide has now dissolved into solution. Next step is to pour it into our mold, into our tinfoil mold here, and then set it on the hot plate so that we can heat it for 45 minutes. Okay, so now we've got our solution. Set it onto our hot plate, and of course we're going to bring our snorkel into position. So if we have any off-gassing, any fumes, that'll be taken care of. So we're going to let this heat for 45 minutes. We'll check back in periodically to see if it's started to congeal. As we continue to heat our polymer, let's go back to our data sheet real quick and see what we've written down. Our starting volume of styrene was 10 milliliters, divinyl benzene 1 milliliter, and we used 100 milligrams of our benzoyl peroxide as our radical initiator. Several times during the course of our 45-minute heating period, we'll take a look back at our polymer as it's setting to see if it's starting to congeal, and then once we get to the end, we'll record our total reaction time. So while we're heating our thermal setting polymer, we're going to go ahead and move over to the synthesis of nylon 610. That's going to be accomplished using a mixture of 2% subical chloride in hexane and 10% 1,6-diaminohexane in sodium hydroxide. We're going to combine 20 mils of each of these components into our 50 ml beaker. We'll have a 2-layer system, and our polymer, our nylon polymer, will form at the interface between the two. That beeping you hear is the hot plate for our thermal setting resin. I'm going to go ahead and pour in my aqueous-based solution first. So this is my 1,6-diaminohexane. Okay, of course I'm doing this underneath the snorkel. This is a very strong smelling components as well, just like we had for our other polymer. Now I'm going to set my stirring rod against the side of my beaker, like so, because what I want to do is I want to pour in this next component so that it will layer on top. We don't want to mix, we actually want a layering impact. I'm going to pull this out to the side just a little bit. And I'm going to do this very gently. I'm going to have to pull our snorkel out so we can see some fumes forming. And then we can see our 2 layers in the beaker. You can see some fumes forming on top, and our nylon polymer will start forming at the interface in between the 2 layers. We'll check back in just a minute. So it's been about a minute, and we're starting to see a film forming at the interface between the 2 layers. So what I'm going to do is I'm going to take a set of tweezers here. I'm going to reach down into the middle, right at the interface, and I'm going to start pulling out the nylon fibers and wrapping them around this test tube. As you can see we formed a thread here. And I'm going to start rotating the test tube up. And as I do this, you should see the volume of the solution, or both solutions, starting to decrease. Now we're stuck to the side of the beaker a little bit. I'm going to try and pull this away, get us back into the middle of the solution. This can be a little tricky to accomplish. Well, it looks like it wants to stay on the side of the beaker, so we'll accommodate it and just keep rotating. We're getting a nice set of nylon thread here on our test tube. When we get done, we'll rinse this off and we'll pull off this loop and take a look at the polymer that we formed. Let's turn our beaker around just a little bit so that we can see what's happened to our volume here. We put 20 mils of each, so we had 40 mils total in the beginning. And now we've drawn those liquids down to about 30 mils total in our beaker. So we are making progress. It's just slow going. Okay, so we've had our first strand break. A significant amount of nylon on our tube. We'll go back into the interface, re-pull the strand, and start rotating again. And that's it. We've wrapped up all of our liquid in the form of nylon 610 threads. We're going to take this over to the sink and rinse it off, and then we're going to test its tensile strength, take a look at it, describe it on our data sheet, and we'll be ready to go. Then we're going to check back in on our thermal setting resin. Now that we've finished pulling up our nylon fibers, before we go wash them off, let's take a look at our data sheet and do a quick recap. We started out with 20 mils of our 1,6-diaminohexane sodium hydroxide solution. That was our aqueous solution, bottom layer. We then added in 20 mils of our subalkyl chloride and hexane. That was our top layer. And it took us around 1 minute to start to see a film forming at the interface between the two layers. Now we're going to go wash the fibers off, remove them from the test tube, and do a tensile strength test. So we have our nylon spooled onto our test tube. We're going to go ahead and rinse it off with a little bit of tap water just to remove any residual solvent. We got quite a bit out of that beaker, as you saw over the course of our time lapse. Every single bit of both of our liquids was converted into our nylon thread, and this is a nylon 610 blend. I go ahead and slide it off the test tube. I'll rinse the inside of the mass as well. And you can see when looking down through the center, you can see some of the fibers. It makes it a little bit more obvious that we're dealing with true fibers here. This isn't just a blob of some amorphous polymer. This is actually threads of our nylon fiber. Okay. Pull apart sections of it here. Let me just give it a final rinse, and then we'll take a little bit closer look at it. I'm going to dry it off just a little bit, and then we'll start pulling it apart. So we finished rinsing our nylon fiber, and I placed it on the bench top here. And as we can see, as we start to pull it apart, you can see the loops of nylon thread that we formed as a result of the reaction. All right, so this is a thread, a looped thread that we pulled up on our test tube. We went from two clear solutions of our starting materials to an opaque white polymer thread of our nylon 610. From a tensile strength standpoint, this is fairly brittle, right? It does hold together, and you can imagine that if these fibers were woven together the way that they would be in clothing fabric, that they have significant group tensile strength, but individual strands are very, very weak. The surface texture right now is still a little bit slimy, right? What we were rinsing off previously was any slight residual starting material, very small amount, and the HCl that's formed as a result of our condensation polymer, right? That HCl comes from our subalkyl chloride pairing with our amine, so we end up forming an HCl that needs to be rinsed off before we can safely handle it. So this is our nylon 610. We'll go ahead and write this down on our data sheet and go check on our thermal setting resin. So we're checking back in with our thermal setting polymer. It's been going for about 55 minutes. I'm going to take it off of the hot plate and we'll take a look down through the top. It's a little bit difficult with the tinfoil reflecting, but what we have, and I'll use the spatula to show this, is a solid puck of our polymer. I'm going to take it out of the form so we can see it a little bit more easily, but we started out with two transparent, colorless liquids. Now we're left with a solid polymer after about 55 minutes of reaction time at 100 degrees. So let's see, probably the simplest way to do this will be to take our cup out. Now, as you can see with our beaker, we had a little bit of it leak out into the cup, but even that has solidified. We'll take our tin foil and we'll open it up on one side. and we get a better look at our polymer. Now the smell is significant, so I'm going to go ahead and move our snorkel over to make sure. And I'll hold this up a little bit. Okay, so this is our thermal setting resin, a clear, solid resin. Brittle, but that's mainly because of the thinness of the layer. If we were to make this a little bit thicker, it would have considerable strength to it. But that's our thermal setting polymer. Let's go make some indications on our data sheet. So we'll do a final recap of our data sheet. We just added our total reaction time, which was roughly 55 minutes for our thermal setting polymer. It was a clear, solid polymer, thin and brittle. Clear, also elaborated, was transparent, as you can see on the video. So clear, transparent, solid polymer, thin and brittle, cracks and breaks very easily, but with a very strong odor. For our nylon, we've added both our tensile strength description and our appearance and surface texture. So our nylon 610, relatively weak single strands, multiple strands resulting in improved tensile strength and resistance to breakage. Much more difficult to pull it apart when you had a group of strands as opposed to a single strand. They were opaque white fibers with a slimy texture when damp, no noticeable odor. And that's all we need for our data sheet. The next part will be filling out our questions for our worksheet. Good luck.